I consider myself as not very lucky. It's already the last day of the conference, and everybody is tired and lunchtime. So I would like to put some nice picture of macaroni, so at least to attract people attention anyway. I will be fine. So my name is Mohammed. I am a PhD student in Evolutionary University. Today I'm going to present some piece of work on cooperative object transport using evolutionary swarm robotics. So first I will introduce the work and some motivation why we did this study. Then I will explain the task and the simulation model, then the methodology and the experiment setup. Then we will see some results we are achieved out of this piece of work. Then I will conclude and I will tell you my future plan. So in multi-robotic system, cooperative object transport is defined as coordinated response of a group of robots in order to collect and retrieve an object that is too heavy to be transported by a single robot. In swarm robotics, cooperative object transport is particularly a challenging task because the swarm agent has to cooperate in order to transport a large object without using any means of centralized control or global information. And when it comes to the real natural swarm, particularly ants display a very effective behavior when it comes to the cooperative object transport through overcoming the distribution of the porter around the body and again to coordinate their action and forces around the object such that they avoid to work against each other. So the swarm roboticists try to mimic this behavior of natural swarm by looking at the individual rules of the natural swarm that generate this impressive global response. So the motivation that since there is a limited research on the cooperative object transport with evolutionary swarm robotics, so this motivates us to investigate this method more with this task. And these limited literature show many obstacles in terms of sensitivity to the object length, object shape, and the size of the swarm. So our long-term objective to show that the evolutionary swarm robotics can help to overcome some of these problems. And the main thing in our study is to investigate the effect produced by the characteristic of the robot sensory apparatus on the design of a group transport for simple swarm robots that can only push the object. So here is the simulation snapshot that we have developed. The task is a group of 2 robots are required to transport an elongated cuboid object that is too heavy to be transported by a single robot. So from the starting position of the robot can perceive the object with their camera, this pink ray, and when they are sufficiently close to the object, they can perceive the object with their infrared sensor, the white rays. So when the robot is sufficiently close enough to the object, they have to coordinate their action on the object such that they exert the forces that cause the robot to move, that cause the object to move, sorry. So from its starting position as far as possible in arbitrary direction. So this is the simulation we have designed, the simulation integrated with body physics engine in order to integrate the dynamic properties of the system because the task requires such physics property. So our simulation, our experiment setup contains of 2 evolutionary conditions. One is NT condition and the second is T condition. In NT condition, the robot uses only a camera and 8 infrared sensor. However, in T condition, the robot uses, in addition to the camera and 8 proximity sensor, 2 torque sensors. Our robot model, the impact robot, we conduct a 26 evolutionary run for each condition. So for NT condition, 26 evolutionary runs, same with P condition. And each one lasts for 4,000 generations. So this is the robot controller, a simple continuous time recurrent neural network. In case of NT condition, there is only 11 input, 8 infrared sensor and 3 camera sectors, so the camera is divided into sectors. While in T condition, there is a 13 input to the neural network, additional left and right torque sensor. The output neuron are 4 neurons control the left and right motor of the robot, wheels. The output neuron and the input neuron are completely reactive. However, the internal neuron maintains some internal state through the recurrent connection. So this graph shows incomplete connection. So we show only the connection for the one node in each layer. So node 1 and node 14. This is only for clarity reason. The same controller copied in all the robots in the swarm. So the swarm is homogeneous. So the evolutionary algorithm is simple GA with rotate wheel selection to evolve the neural network parameter. So we evolve only the weights of the neural network, which I have shown you previously. And the fitness function contains of 3 components, F1 and F2 and F3. So F1 reward the group in which approach the object and attach to it. F2 reward a transportation of object at maximum speed. However, F3 reward a transportation of object as far as possible from its starting position to the final position. Both F1 and F2 evaluated each simulation time stage, so they are local. However, F3 are evaluated at the end of each trial. So the trial lasts for 600 simulation time steps, which is equal to 60 seconds, so the simulation steps 10 times a second. So this is the result comparison between the torque and non-torque sensor. Here is a 26 runs for each evolutionary condition. White bar represents the NT condition, gray bar represents the T condition. In each bar, there is a 567 trial represent the performance which measure in terms of the distance the object has been transported, as shown in y-axis. So these runs are sorted by the performance from best to worst. As expected, the T condition outperformed the NT condition, which is shown by Wilkerson test that showed a significant difference between the two results. And we will see in a minute through visually inspected the solution. Here is the NT controller can be successfully transported into real robots. So here is for EPAC. Work together to transport the green box. So you can see the robot can transport the object in different formation, like assembly, or they can directly attach to the object and push it directly. So they change this formation. But unfortunately, the solution with NT condition is poor. Why? Because you can see here, because the NT condition controller, when they see the robot, they move towards the robot and they push the robot at the maximum speed. Okay? Those robots has no means to distinguish between the action that produce a successful object movement from those that not. Okay? So they keep on blindly pushing the object and fall in a deadlock where those robots couldn't recover from, as seen in this video. So, however, the T condition outperforms the NT condition. Why? Because those robots exploit the extra sensory information provided by the torque sensor to have a feedback information about whether the current action on the object produce a successful object movement or not. Such robots, when they see the object, they move towards the object and push the object. If the object doesn't move, and this is indicated by the information of the torque sensor, so if the torque sensor say there is no successful object movement, the robot back up and try a different position and keep on doing such until the effective distribution of force on the object is generated and the object is moved. Or the agents see the other nesmate and move towards the nesmate, so they assemble in one direction of the object and they restart the pushing behavior such that they can succeed to push the object as far as possible. I will come back to this in a moment. So the robot with decondition could recover from deadlock by exploiting this extra information of torque sensor, and they could distinguish between whether their current action is useful or not. So since the decondition is better than a decondition, so we go ahead and select the best group out of 26 runs in decondition, and this post-evaluation test. So each graph represents a homogeneous group of 2 and 3 and 4 robots while pushing the object of different mass, as shown in x-axis. Again, the performance in terms of the distance that the object has been transported in meter, as shown in y-axis. So there is a common trend between these three graphs where the heavier the object, the less distance achieved. And this is obvious. We have conducted a linear mixed model test to see the relationship between the mass and the length and the group cardinality. And the interesting thing is using this test, it shows no significant difference with the group cardinality, which is good, though the size of this one is small. But the longer the object, the lower the performance is. And through visually inspecting the solution, we can say that this is a reason why when the robots try to push the object and the object doesn't move and they back up and they keep on attaching different positions, so the longer the object, so the longer the time required to effectively distribute the forces across the object and ultimately move the object. So the less time left for the transportation. And as recall that the transportation is in terms of the distance the object is being pushed. There is another interesting test called recruitment-test. As I mentioned, that there is a tendency for the robot to move to the nesmate, okay, when they couldn't move the object. So here we change the operational condition where two robots and the object of 20 centimeter and 280 grams. So we got two robots. One robot is mobile robot and the second robot is frozen robot. The mobile robot extended the camera vision to 1 meter. However, the frozen robot gave the same range, which is 50 centimeter, the original range. The frozen robot will not move until the mobile robot get to the object, try to move the object. If the object doesn't move, then move close to the nesmate, then the frozen robot activated. However, even the frozen robot is activated. It has no means to get to the object. Why? Because we place the frozen robot 80 centimeters away from the object. So the vision range is 50 centimeters. So they have no means to get to the object, and it's being guided by the mobile robot. So this video could show this behavior clearly. So even this video could show the T condition where it's reposition and realign when the object couldn't move. So when they see the nesmate, they move towards the nesmate. The nesmate activated, but has no means to get to the object, so they just rotate. But it's follow the mobile robots, and they order us to move the object. We did this test for all 26 runs with T condition to figure out how many to the best group in each run. So how many of these groups are developed such a kind of simple recruitment behavior. So, in conclusion, I would say that I have shown you that the T-condition robot, the robot which equipped with the torque sensor, can display a robust performance in terms of variability of the object length and the object mass and the group cardinality and the starting position and orientation. So this robot show fairly robust performance when it comes to this parameter. Why? Because it exploits this extra sensory information provided by a torque sensor as a valuable information to evaluate their current action on the robot, whether it's produce a successful object movement or not. So this information provided by torque sensor help the robot to recover from the deadlock in case of T condition. And this shows that a small change in a sensory motor configuration of the robot can help the evolution to find a robust solution and adapted solution. So again, back to the original goal. So we want to investigate the evolutionary Chuan robotics and whether it can generate an effective solution when it comes to the group object transport and the characteristic of the sensory system of the robot. And I have shown you this simple form of recruitment behavior. This recruitment behavior, we haven't engineered for this recruitment behavior. Means our fitness function, the experiment design, doesn't have any mean of providing the recruitment behavior. So this is the recruitment behavior generated for free. So this, again, suggests that the evolutionary Chuan method offer the opportunity to serpentitas object or behavior that improve the adaptability of the system. So, though we haven't engineered for the simple recruitment test, we got this behavior for free, according to the nature of the task. So the robot moves towards the next mate and recruit the next mate towards the object. So this is the present work. Again, we show that the T condition outperform anti condition. Anti condition can be transferred to the real robot. However, T condition cannot. Why? Because the EPAT robot, which I have shown you, doesn't have a torque sensor. So still, there is a reality gap. So for this reason, we go and investigate using an alternative sensor, and we develop this sensor, an optical mouse sensor that gives you an X and Y displacement information. And we place it in the position of the battery and add an extra extension on top of the robot to move the battery on top. And we use in simulation, we use this sensor as just a switch to tell the robot whether it's currently moving or not. And using just this simple information, with this sensor, we got a similar, as good as a result with torque sensor. So what we did, we just remove the left and right torque sensor. We feed one input with zeros or one when the robot is moved, zero if the robot doesn't move. So we got similar results. So this is again that the evolutionary could exploit any extra sensory information towards finding the path to effective solution. And the future work is to try to increase the size of the swarm. So because we think that for robot is not that swarm-like, but anyway, we already increased the number to 8 robots, but the performance is dropped because these robots are not designed for such transportation behavior, because we end up with many robots pushing each other in the same structure, and these physics cannot be maintained. So it will be difficult. But anyway, we'll try to increase the number of swarm. Then, with the current work, the object is transported in an arbitrary direction. We want the object to move towards a source location, a nest location, and we currently as well use the range and bearing sensor to do the nesting behavior. We also want to try to investigate using the communication using range and vary that affect the transportation strategy. And again, we want to investigate the irregular shape. So we try to increase the complexity of the task, and we want to see whether the evolution can cause such complex behavior or not. So, thank you for your attention. That's it.